You are moving right now, 230 kilometers per second, around something 26,000 light years away. You have been doing this your entire life. Your parents did it. Every ancestor you have ever had. Every human who ever lived. Every star you have ever seen in the night sky. All of it. 200 billion stars, gas clouds, planets, everything in the Milky Way, moving in vast, patient orbits around the same invisible center. At that center sits a supermassive black hole, 4 million times the mass of the Sun. And for most of human history, we didn't know it was there. Tonight, we are tracing the story of Sagittarius A star, the invisible center of everything we know, the dark heart of the Milky Way. If this quiet journey brings you even a moment of peace, I am truly grateful you are here. A gentle like or a soft tap on subscribe helps me keep creating these night voyages for curious minds and tired souls. Let us begin. Part 1. The dark, heart we couldn't see. For thousands of years, people looked up and saw the Milky Way as a band of light stretched across the sky. Faint, diffuse, beautiful, but just light. A glow so familiar, so constant that most people stopped asking what it was. By the early 1900s, we understood what it was. A galaxy. Spiral, vast, with us sitting on one side, about 2/3 of the way out from the center. We assumed there was a center, some dense region where stars pulled together. But we thought it was just more stars, closer together, brighter. Nothing special, nothing extraordinary. The problem was visibility. Between us and the galactic center, enormous clouds of gas and dust block optical light completely. When you look toward Sagittarius with a normal telescope, you see nothing but darkness. Not the darkness of empty space, but the darkness of something blocking the view. A curtain of dust, billions of kilometers thick, drawn across the center of our own home. For centuries, the heart of the Milky Way was hidden from us. It was there. It had always been there, but we couldn't see it. Then, in the 1970s, radio telescopes began scanning the galactic center. Radio waves pass through dust. They don't care about the curtain. And they found something strange, a powerful, compact radio source, bright, concentrated, unmoving, too bright to be starlight, too small to be a star cluster, too concentrated to be gas. It sat there in the radio sky, steady and intense, like a beacon that had been calling out for billions of years. And we had only just built ears to hear it. The discovery was made in 1974 by astronomers Bruce Ballack and Robert L. Brown using the Green Bank Interferometer in West Virginia. They named the source after the constellation where it appeared, Sagittarius A, and then, in 1982, Robert Brown assigned it the asterisk Sagittarius A star. The asterisk, in radio astronomy notation, signifies a compact, non-thermal source. Something massive was there, something invisible, something pulling everything toward it. But you can't see a black hole, you can only see what it does. And what it does was about to become one of the most extraordinary stories in the history of science. Part 2. The most patient experiment in science. In the early 1990s, two teams of astronomers began one of the most patient and determined experiments in the history of science. The Keck Observatory in Hawaii, sitting atop the dormant volcano Mauna Kea at an altitude of nearly 4,200 meters above sea level, where the air is thin and the atmosphere is stable and the stars barely twinkle at all. And the Very Large Telescope in Chile, perched on the summit of Cerro Paranal in the Atacama Desert, one of the driest and most remote places on Earth, a facility of 4 giant 8-meter mirrors and dozens of smaller auxiliary telescopes spread across a mountaintop. Both teams aimed their instruments at the same patch of sky, the galactic center. Using infrared cameras, watching in wavelengths our eyes can't see, wavelengths that can penetrate the dust clouds that block visible light. And they tracked individual stars, not hundreds of stars, not a statistical survey of thousands, a few dozen specific, named, watched year after year, image after image, season after season, decade after decade, watching them move. And the stars moved fast, not the slow drift you would expect from distant objects. These stars were whipping around something invisible, like planets around the sun, but far more extreme. Tight orbits, elliptical, violent, accelerating. Behavior that could only mean one thing, something impossibly massive sat at the center of those orbits. One star became the key, a blue-white star. Unremarkable in its appearance, except for where it was and how it moved. The Keck team designated it S02. The European team called it S2. Both teams were watching the same star, and S2's orbit would prove everything. S2 orbits Sagittarius A star every 16 years. That is extraordinarily fast for something orbiting the center of a galaxy. Our Sun takes 230 million years to complete one orbit. S2 does it in 16. Let that sit for a moment. The Sun's orbit takes 230 million years. S2's orbit takes 16. At periapsis, the point where S2 comes closest to the black hole, it gets within 17 light hours of Sagittarius A star. For context, Neptune is about 4 light hours from our Sun. S2 gets 4 times closer to a black hole than Neptune is to the Sun. And at that distance, it accelerates to about 2.7% of the speed of light, around 7,650 kilometers per second. Fast enough to cross the distance from Earth to the Moon in less than a minute. Scientists followed S2 for decades, tracking its motion year after year. They watched it sweep past the black hole in 2002, and then waited, and waited, and watched it sweep past again in 2018. One full 16-year orbit, from close pass to close pass. Frame by frame, year by year, they could see it accelerate as it approached periapsis. They could see it decelerate as it moved away. They could see the orbit precess, the ellipse itself rotating, exactly as Einstein's general relativity predicted for motion in a powerful gravitational field. The path was perfect. Keplerian, exactly what you would expect from an object orbiting a massive point source, and the teams did the mathematics. To make a star move that fast, in an orbit that tight, there had to be something incredibly massive at the center, concentrated in a space smaller than Mercury's orbit around the Sun. The numbers were precise. Roughly 4 million solar masses, 4 million times the mass of our Sun, compressed into a region so small it would fit inside our solar system. No star cluster could be that dense without collapsing. No gas cloud could stay together under that kind of gravity. No normal object could hide that much mass in that little space. Only one thing fit the evidence: a supermassive black hole. By 2002, the case was essentially closed. Sagittarius A star wasn't just a radio source, it was a black hole. Our black hole. The two team leaders, Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics and Andrea Ghez at UCLA, were awarded the Nobel Prize in Physics in 2020, sharing it with Roger Penrose, who had proved mathematically that black hole formation is an inevitable prediction of general relativity. Decades of patient observation, thousands of images, millions of calculations, all confirming what the radio signal had first hinted at half a century earlier. Something massive and invisible sat at the center of the Milky Way, and now we had its name. Part 3, S2 and the Proof of Einstein. By the time S2 made its 2018 periapsis passage, the instruments had improved dramatically. The European team was now equipped with gravity, a 4-telescope interferometric beam combiner at the Very Large Telescope, capable of combining the light from all 4 of the VLT's giant mirrors simultaneously. The result was the equivalent resolution of a single telescope, 130 meters in diameter. They were ready, and what they measured, as S2 swept within 17 light hours of the black hole, was not just an orbit. It was a test of Einstein's general theory of relativity in the most extreme gravitational environment accessible to us. Einstein had predicted that light emitted by an object in a strong gravitational field should be stretched to longer wavelengths, shifted toward the red end of the spectrum. This is called gravitational redshift. It doesn't exist in Newton's theory of gravity. It only exists in Einstein's, and if S2 showed it near periapsis, it would be the first direct detection of gravitational redshift near a supermassive black hole in the entire history of astronomy. They watched S2 approach periapsis in May 2018. They tracked its position across the sky with astrometric precision, measured in micro-arcseconds, a unit so small that it corresponds to seeing a €2 coin at the distance of the Moon. They measured its radial velocity toward and away from Earth via its Doppler shift. And they watched the light of the star stretch, reddening by an equivalent of about 200 kilometers per second as it clawed its way out of the black hole's gravitational well. The data were inconsistent with pure Newtonian dynamics at a confidence of 5 sigma, the gold standard of physics. The results matched Einstein's general relativity. Precisely, exactly, as predicted. Not approximately, exactly. 2 years later, in 2020, the gravity team published another result: the detection of Schwarzschild precession in S2's orbit. The axis of the orbital ellipse had shifted by 12 arc-minutes per orbit, exactly as Einstein's equations predicted for a massive object orbiting in warped spacetime. This was yet another pillar of general relativity, confirmed in the most extreme natural laboratory we have ever found. S2 became, in the words of astrophysicist Frank Eisenhower of the Max Planck Institute, the ideal black hole laboratory. A single blue-white star, orbiting an invisible monster every 16 years, giving Einstein's century-old theory its most rigorous test yet around a massive object. And the theory passed, every time, without exception. Part 4. The first photograph. For decades after the confirmation of Sagittarius A star as a black hole, we knew it was there. We could measure its mass, track stars orbiting it, map its gravity, predict its behavior. But we had never seen it, not directly, not visually. The closest supermassive black hole to Earth, the one we orbit, remained invisible. In 2019, the Event Horizon Telescope changed that. Not for Sagittarius A star, not yet, but for the first time in history, a black hole had been photographed. The Event Horizon Telescope is not a single instrument. It is a planet-sized network of radio observatories spread across 8 geographic sites on 6 continents: Chile, Hawaii, Arizona, Mexico, Spain, and the South Pole. Each observatory is individually capable and scientifically productive. But together, synchronized by atomic clocks, and connected by the technique of very long baseline interferometry, they function as a single virtual telescope with a baseline equal to the diameter of the Earth. The angular resolution of this Earth-sized instrument is extraordinary, fine enough to resolve an object the size of a donut on the surface of the Moon as seen from Earth, or equivalently, to read individual letters in a newspaper in New York while standing in Los Angeles. In 2019, the EHT turned this instrument toward M87, a giant elliptical galaxy 55 million light-years away, hosting a black hole 6.5 billion times the mass of the Sun. And they produced the first image of a black hole event horizon ever captured. a glowing ring of hot gas, bent into a luminous circle by extreme gravity, surrounding a dark shadow where light was being swallowed. The image traveled around the world in hours. People stared at it the way people might stare at the first photograph ever taken of a continent they had only seen on maps. And then, in May 2022, the EHT collaboration released a second image, this time closer to home. Sagittarius A star. It had taken longer, and the reason was extraordinary. M87 star is massive and relatively stable. It changes, slowly, over days or weeks. Its enormous size means that even with its tremendous activity, the light that escapes its environment is averaged over a timescale that allows image reconstruction. Sagittarius A star is smaller, and it flickers. Gas swirls around it on timescales of minutes to hours. The brightness shifts constantly, erratically, like a flame in wind. As the EHT scientists described it, attempting to photograph Sagittarius A star is like trying to photograph a child who will not sit still. Except that the child is also 26,000 light-years away. The teams had to develop entirely new computational techniques to handle the variability. Rather than constructing a single image from the night's data, they had to average together thousands of possible images generated by different computational methods, keeping only the features that consistently appeared across many reconstructions. The final image was built from data collected by 8 observatories in April 2017, processed over 5 years of calculation. But the teams had it. A bright ring of hot gas, its light bent into a circle by the curvature of space-time around the event horizon. And in the center, a shadow, a dark silhouette, 52 microarcseconds across. The event horizon of Sagittarius A star, seen for the first time. For the first time in history, we saw the face of the thing we had been orbiting our entire lives. Part 5. What 4 million solar masses actually means. The image was released. The confirmation was complete. And immediately came the question that anyone who stopped to think about it would ask. What does 4 million solar masses actually mean? Let us build the scale from the ground up. Our Sun, the ordinary middle-aged yellow dwarf star at the center of our solar system, is 1.4 million kilometers wide. If you could somehow drive a car at highway speed without stopping, you would need about 160 years to drive across it. It contains 99.8% of all the mass in the solar system. Its gravity holds 8 planets in orbit across billions of kilometers, with such precision that we can predict planetary positions thousands of years in advance. Now imagine compressing that sun, that 1.4 million kilometer wide ball of nuclear fusion, into a black hole. At solar density, it would have an event horizon about 3 kilometers across. A tiny sphere, smaller than a city, containing the mass of an entire star. Now do that 4 million times. 4 million suns, each compressed to a singularity. All of it crushed into a single point, or more precisely, into a region smaller than Mercury's orbit around the Sun. The event horizon of Sagittarius A star is approximately 17 million kilometers in diameter. That sounds large, until you remember that Mercury orbits the Sun at 77 million kilometers. The event horizon of our galaxy's central black hole fits inside Mercury's orbit with room to spare, and in the space of that event horizon sits 4 million solar masses, 1.3 trillion Earths. If you somehow lined up planet-sized objects, each one as massive as Earth, you would need 1.3 trillion of them to equal Sagittarius A star's mass. Lined up edge to edge, that chain would run to the nearest star and back about 200 times. The Schwarzschild radius, the mathematical radius at which any mass becomes a black hole, for a sun mass object is 3 kilometers. For Sagittarius A star, it is approximately 12 million kilometers. But because Sagittarius A star is spinning, Rapidly, as we will see, the effective event horizon is slightly smaller. Everything within that boundary is gone from the observable universe, not just invisible, but physically absent from space-time. Your year inside the event horizon orbit would last just over 4 hours. That is the orbital period at the innermost stable circular orbit, the closest distance a particle can orbit without inevitably spiraling inward. 4 hours, one complete orbit around a black hole, where it takes the Earth 365 days to orbit the Sun. For comparison, consider the scale of known black holes. Sagittarius A star, 4 million solar masses. M87 star, the black hole photographed first in 2019, 6.5 billion solar masses. TON 618, one of the largest black holes ever discovered, 66 billion solar masses. TON 618 is 16,000 times more massive than Sagittarius A star. By comparison, our galaxy's black hole is tiny, but tiny is a relative term. 4 million suns, 1.3 trillion Earths, incomprehensible mass, crushed into infinite density. And it is the closest supermassive black hole to Earth. Part 6. What is a black hole, really? Most people have heard the word. Few have thought carefully about what it means. A black hole is not a hole. It is not empty space. It is an object, the most extreme object that physics predicts can exist. A region where mass is so concentrated that the escape velocity exceeds the speed of light. The escape velocity from Earth's surface is about 11 kilometers per second. Rockets must exceed this speed to break free of Earth's gravity. The escape velocity from the Sun's surface is about 617 kilometers per second. The escape velocity from the surface of a black hole is greater than 300,000 kilometers per second, the speed of light. Since nothing can travel faster than light, nothing can escape. Not matter, not energy, not information of any kind. The boundary at which the escape velocity equals the speed of light is called the event horizon. It is the point of no return. Not a physical surface. There is nothing there you could stand on, no wall you would feel, but a mathematical boundary in space-time, beyond which the future of every particle, every photon, every bit of information is directed inward, toward the singularity. From outside the event horizon, a distant observer watching an object fall in would see something strange. As the object approaches the event horizon, the light it emits takes longer and longer to climb out of the gravitational well. Time slows. The object appears to redden, to fade, to asymptotically freeze at the horizon, never quite crossing it from the outside observer's perspective. But from the infalling object's perspective, nothing dramatic happens at the horizon itself. There is no wall, no visible boundary. General relativity tells us that the event horizon is detectable only globally. You cannot determine your position at the horizon from local measurements alone. You simply pass through it, and only afterward do you realize there is no way back. Inside the event horizon, the geometry of space-time is inverted. What was the spatial direction inward, toward the singularity, becomes the temporal direction, the future. Falling toward the singularity is not just movement through space. It is movement through time, toward an inevitable future. You cannot choose not to hit the singularity any more than you can choose not to experience tomorrow. At the singularity itself, the curvature of space-time becomes infinite. The known laws of physics break down. General relativity predicts infinite density, infinite curvature, the end of the geodesics, the paths that particles follow through space-time. In the words of the Stanford Encyclopedia of Philosophy, particles following such paths would run out of world. What happens at the singularity, our current physics cannot describe. It is the edge of the map. Beyond this point, we do not yet have the mathematics. Roger Penrose sharing, the 2020 Nobel Prize, proved mathematically that once a trapped surface forms, a region where all light converges inward, The formation of a singularity is inevitable. No special symmetry required. No fine-tuned conditions. Under very general assumptions, general relativity requires that singularities exist. And since we cannot violate the laws of physics to look inside one, Roger Penrose also formulated the cosmic censorship hypothesis, the conjecture that all singularities must be hidden behind event horizons, that the universe, in its decency, hides its infinities. Sagittarius A star is not a non-rotating black hole. It spins, and for rotating black holes, the singularity is not a point, it is a ring. A ring singularity sitting in the plane of rotation, surrounded not by one event horizon but two, the outer event horizon and the inner Cauchy horizon. And outside the outer event horizon, there is something even stranger, the ergosphere. The ergosphere is a region of space around a spinning black hole where space-time itself is dragged around by the rotation. The phenomenon is called frame dragging, predicted by Einstein, confirmed by NASA's Gravity Probe B experiment. Within the ergosphere, it is impossible to remain stationary relative to the distant stars. Space-time itself is rotating faster than the speed of light at the ergosphere boundary, though no matter moves faster than light locally. Inside the ergosphere, but outside the event horizon, you could theoretically escape. But you cannot stand still. You are caught in the current. Part 7. A spinning black hole shaped like a football. We have known for decades that Sagittarius A star is there. We have photographed it. We have measured its mass. But one of its most fundamental properties remained uncertain for a long time. How fast is it spinning? A black hole has only two intrinsic properties, mass and spin. Everything else about it is hidden behind the event horizon, inaccessible to the universe outside. The mass of Sagittarius A star was well established, approximately 4.3 million solar masses, confirmed by multiple independent measurements. But its spin rate was harder to pin down. Measuring the spin of a black hole requires observing the behavior of matter extremely close to the event horizon, in the region where the effects of rotation are strongest. In January 2024, a team led by Ruth Daly of Penn State University published results in the monthly notices of the Royal Astronomical Society that settled the question. Using a new technique called the outflow method, combining X-ray data from NASA's Chandra X-ray Observatory with radio data from the Carl G. Jansky Very Large Array, they measured how material was flowing toward and away from the black hole and used that flow to infer the spin rate. The result was remarkable. Sagittarius A star is spinning at approximately 60% of the maximum possible spin rate. The maximum spin rate is the limit set by special relativity, the point at which the event horizon would be moving at the speed of light. Sagittarius A star is rotating at 60% of that limit. Its angular momentum is about 90% of the theoretical maximum. At that spin rate, the space-time surrounding the black hole is dramatically warped. A rotating black hole drags space-time around with it, an effect called frame dragging. The faster the spin, the more extreme the frame dragging. And at 60% of the maximum, the effect is powerful enough to squash the shape of space-time itself. Viewed from the top, looking down along the axis of rotation, the space-time around Sagittarius A star looks circular. But viewed from the side, the surrounding space-time is shaped like an American football. Compressed at the poles, bulging at the equator, distorted by the sheer momentum of the rotating singularity inside. The faster the spin, the flatter the football. Ruth Daly of Penn State summarized it. Our results indicate that Sagittarius A star is spinning very rapidly, which is interesting and has far-reaching implications. One of those implications concerns the future. A spinning black hole is, in the words of co-author Binny Sebastian of the University of Manitoba, like a rocket on the launch pad. Once material gets close enough, it's like someone has fueled the rocket and hit the launch button. Right now, Sagittarius A star is relatively quiet. There is limited material in its immediate vicinity, not enough to sustain significant accretion or powerful jets. But if the amount of material in its environment increases, if a gas cloud drifts too close, if a star is torn apart by tidal forces, the spin energy could be extracted through the Blandford-Znajek mechanism, launching powerful jets of material from the poles. When might that happen? In 1,000 years? In 1,000,000 years? Perhaps in our lifetimes. No one knows. But the fuel is there. The engine is running. And it is spinning fast. Part 8. The Quiet Monster. Why Sagittarius A star is strange. When most people imagine the black hole at the center of a galaxy, they imagine something violent. A quasar, a blazing beacon visible across billions of light years, devouring entire solar systems every year, outshining its host galaxy by a factor of 1,000, the most powerful sustained energy sources in the universe. Active galactic nuclei, galaxies whose central black holes are actively accreting, radiating, and in many cases launching enormous jets of matter and energy that can stretch for millions of light years. Sagittarius A star is none of these things. Most of the time, it is quiet, starved, a giant with its mouth closed, a supermassive black hole at rest. The reason is environment. The amount of matter falling into Sagittarius A star is extraordinarily small compared to the active galaxies we observe from afar. As NASA's Chandra X-ray Observatory data reveals, less than 1% of the material that enters the black hole's gravitational influence actually reaches the event horizon. Most of it is ejected, flung outward by magnetic fields and radiation pressure before it can cross the point of no return. The result is a black hole that, by the standards of active galactic nuclei, is essentially dormant. The luminosity of Sagittarius A star in X-rays is approximately 10 to the power of 33 ergs per second. The luminosity of a typical quasar might be 10 to the power of 46 ergs per second. Sagittarius A star is 1 trillion times less luminous than a typical quasar. It is one of the faintest supermassive black holes known relative to its mass. But occasionally, even quiet Sagittarius A star wakes up briefly. On May 13, 2019, astronomers using the Keck Observatory witnessed a sudden brightening of Sagittarius A star. It became 75 times brighter than usual over the course of a few hours. The cause is thought to be the passage of another object, perhaps a gas cloud, perhaps a smaller compact body, through the inner accretion region, temporarily feeding the black hole and triggering a flare. In June 2023, unexplained filaments of radio energy were found associated with Sagittarius A star, mysterious structures extending from the galactic center whose origin is still being investigated. These flares are temporary, brief awakenings of something that is mostly asleep. But they remind us that even in its dormancy, Sagittarius A star is not truly inactive. It flickers, it fluctuates. Gas swirls around it on timescales of minutes to hours, heated to millions of degrees by the friction of infalling material. The ring of light we photographed in 2022 glows at temperatures that would vaporize any known material instantly. And when a cloud drifts close enough or a star wanders too near, the monster stirs. This quiet state may not always have been the case. A 2011 study using ESA's Integral Gamma Ray Observatory found evidence, preserved in the surrounding Sagittarius B2 molecular cloud, of a powerful outburst from Sagittarius A star that occurred roughly 300 years ago. The total luminosity of that outburst is estimated at about 1.5 times 10 to the 39th ergs per second, 1,000,000 times stronger than the current output, comparable to a typical active galactic nucleus. 300 years ago, someone with the right telescope would have seen a very different galactic center. And evidence published in September 2024 by researchers from the Nevada Center for Astrophysics at UNLV suggests something even more dramatic in the deeper past. Sagittarius A star's spin is unusually rapid, and its rotation axis is misaligned with the angular momentum of the Milky Way. The UNLV team demonstrated that these unusual characteristics are best explained by a major merger. Sagittarius A star consuming another supermassive black hole, likely from a satellite galaxy that the Milky Way swallowed long ago. The merger would have dramatically altered both the spin rate and the spin axis of our galaxy's central black hole. In the words of lead author Yihan Wang, this discovery paves the way for our understanding of how supermassive black holes grow and evolve. The dark heart of our galaxy carries within the memory of a collision, a consuming of an entire other galaxy's worth of darkness, merged into the one we now orbit. Part 9. The Light That Hasn't Arrived Yet. Sagittarius A star is 26,000 light-years away. Not 26,000 kilometers, not 26,000 miles, 26,000 light-years. 1 light-year is approximately 9.5 trillion kilometers. 26,000 light-years is approximately 247 quadrillion kilometers. It is a distance so vast that writing it as a number conveys almost nothing. The implication is this: when we look at Sagittarius A star, we are not seeing it as it is now. We are seeing it as it was 26,000 years ago. The light that produced the image released by the Event Horizon Telescope in 2022 began its journey to us in the year approximately 24,000 BCE. Think about where human civilization was at that moment. Modern humans had been on Earth for about 274,000 years, having appeared in Africa during the Middle Stone Age. The most recent ice age was still underway. The Laurentide ice sheet covered much of North America under kilometers of ice. The climate was about 6 degrees cooler than today across much of the northern hemisphere. Small bands of Homo sapiens were living as hunter-gatherers in Africa, Europe, and Asia, just beginning to develop sophisticated cave art. The first permanent settlements were still 10,000 years in the future. Writing had not been invented. Agriculture had not begun. The cities of Mesopotamia were 20,000 years away. And those photons we photographed in 2022, that ancient light from the ring around Sagittarius A star, were already on their way to us, traveling through the dust and gas of the spiral arms, through the quiet lanes between stars, through the long dark between galaxies. For 26,000 years they traveled, while civilization rose and fell and rose again, while every word ever written was written and forgotten and found again, while we built telescopes, taught ourselves mathematics, learned to synchronize radio dishes across a planet and call it a single instrument. And only then did those photons arrive, and only then did we have the tools to receive them. Right now, in this present moment, something is happening at Sagittarius A star. Maybe a gas cloud is spiraling inward. Maybe a flare is erupting. Maybe a star is being torn apart by tidal forces and consumed. Maybe it is perfectly quiet. We cannot know. The light that would show us Sagittarius A star as it is right now, in this exact moment, will not reach Earth for 26,000 years. 26,000 years from now. Modern humans appeared roughly 300,000 years ago. 26,000 years is nearly 1/10 of the entire span of human existence. In 26,000 years, human civilization might be unrecognizable. We might have spread across the solar system or across the stars, or we might have long since perished, leaving only the fossil record as evidence we were ever here. The climate will have shifted dramatically. Continents will have drifted measurably. Species will have gone extinct, and new ones will have appeared. The stars in the night sky will have moved to different positions. And only then, 26,000 years from now, will observers, if there are any, See what Sagittarius A star looked like in the year 2026. We are always watching the past, never the present. Everything we know about Sagittarius A star, every measurement, every observation, every image is ancient history, and there is no way around it. Light has a speed limit. Information has a speed limit. We are separated from Sagittarius A star not just by distance, but by time itself, a 26,000-year chasm we can never cross. What is Sagittarius A star like right now? We can't know, not for 26,000 years. All we have is the past, always the past. Part 10. The Ancient Origins. How did it form? The question that follows from the image, from the measurements, from the confirmation of Sagittarius A star's existence, is the question that underlies all of black hole science. How did it get there? The origin of supermassive black holes is one of the great unsolved mysteries of modern astrophysics. We know they exist. We know they sit at the centers of almost every large galaxy we have ever observed. We know they can contain billions of solar masses. What we do not fully understand is how they formed and how they grew so large. The simplest theory is that supermassive black holes are the end product of billions of years of merging and growth. Small black holes, stellar mass black holes formed from the collapse of massive stars, merge and grow. They consume gas from their environments. They swallow companion stars. They merge with other black holes when their host galaxies collide. Over billions of years, through countless mergers and accretion events, they grow from stellar mass to millions or billions of solar masses. But this theory has a problem. The universe is only about 13.8 billion years old, and we have observed quasars, active supermassive black holes with masses in the billions of solar masses, existing when the universe was less than 1 billion years old. Building a billion solar mass black hole through ordinary stellar collapse and gradual merging in less than 1 billion years is extremely difficult. The numbers barely work, even with the most optimistic assumptions. Alternative theories propose that supermassive black holes may have formed from the direct collapse of enormous gas clouds in the early universe, bypassing the stellar phase entirely. Or that they grew rapidly in the dense environments of early galaxies when gas was abundant and accretion rates were far higher than today. Or that they are the remnants of the very first stars, population 3 stars, massive, hot, and short-lived, whose remnants could have served as seeds for rapid growth. The James Webb Space Telescope, looking back to within a few 100 million years of the Big Bang, is beginning to reveal populations of surprisingly massive black holes at the earliest epochs, observations that continue to challenge our formation models. For Sagittarius A star specifically, the UNLV merger study published in 2024 adds another layer. The unusual spin rate and misalignment of the rotation axis suggest that at some point in its history, Sagittarius A star consumed another supermassive black hole from a satellite galaxy that the Milky Way absorbed. The merger would have been a cataclysm, generating gravitational waves powerful enough to propagate across billions of light years. Waves that the planned Laser Interferometer Space Antenna, LISA, expected to launch in 2035, should be able to detect from similar mergers happening in other galaxies today. Sagittarius A star is already ancient when we measure it. It likely formed in the early universe, billions of years ago, when galaxies were young and still assembling. It was already massive, already ancient, already sitting at the center of what would become the Milky Way before our solar system formed 4.6 billion years ago. It was there when life appeared on Earth, when the dinosaurs roamed and died, when the first humans looked up at the night sky. It will still be there long after the sun dies, long after every star we can see has burned out or drifted away into the expanding void. And it has been doing the same thing the entire time, pulling, holding, anchoring, Part 11. What lies beyond the event horizon? No one has ever crossed an event horizon. No signal from beyond one has ever reached us. By definition, it cannot. The event horizon of a black hole is not just a dangerous boundary. It is a fundamental information barrier, a one-way membrane through which knowledge can enter but never escape. And yet, general relativity makes very specific predictions about what happens inside. For a falling observer approaching the event horizon of Sagittarius A star, the approach would, at first, be unremarkable. The event horizon has no physical surface. There is no atmosphere, no wall, nothing to collide with. You simply pass from a region of space-time where escape is theoretically possible to a region where it is not. Einstein's equivalence principle tells us that locally, nothing dramatic happens at the event horizon itself. You cross it. And you do not even know. But then the geometry changes. Inside the event horizon, the direction toward the singularity becomes the future, not just spatially inward, but temporally inevitable. Falling toward it is not a choice you can reverse. It is as inevitable as tomorrow. As you fall inward, the gravitational gradient, the tidal force, increases. Tidal forces arise because gravity is slightly stronger on the near side of an extended object than on the far side. For a small black hole, these tidal forces at the horizon are catastrophic. You would be stretched into a thin strand of matter in a process known as spaghettification before you even crossed the event horizon. But for a supermassive black hole like Sagittarius A star, the tidal forces at the event horizon are actually gentle. The horizon is so large, 17 million kilometers in diameter, that the gravity gradient across a human body is negligible at the crossing point. You would pass through into the irreversible interior without pain, without drama, without any local indication that anything extraordinary had occurred. Only later, as you fell deeper, would the tidal forces grow catastrophic? As you approached the singularity, the curvature of space-time would increase without bound. You would be stretched in the radial direction and compressed laterally. And eventually you would reach the singularity, the ring singularity of a rotating black hole, at which point the mathematics of general relativity breaks down completely. The known laws of physics fail. We do not know what happens. We may never know. The theoretical physicist John Wheeler, who coined the term black hole, described the singularity as nature's ultimate rejection of the laws of physics. It is the place where our best theories simply stop working. Some physicists believe the singularity is an artifact, that a future theory of quantum gravity, combining general relativity with quantum mechanics, will smooth it out into something finite and computable. Loop quantum gravity, for example, proposes that space-time itself is granular at the Planck scale, and that infinite curvature is replaced by an extremely high but finite density. String theory offers similar alternatives. We do not yet know which, if any, of these approaches is correct. What we do know is that Stephen Hawking proved in 1974 that black holes are not entirely black. Quantum effects at the event horizon cause pairs of virtual particles to be produced. One falls in, one escapes, resulting in a slow emission of thermal radiation. This is called Hawking radiation. For a black hole of Sagittarius A star's mass, the Hawking radiation temperature is approximately 10 to the power of -14 Kelvin, far colder than the cosmic microwave background, which bathes the entire universe at 2.7 Kelvin. Sagittarius A star is absorbing far more energy from the surrounding universe than it emits as Hawking radiation. It is growing, not shrinking. But over an almost unimaginably long time scale, if the universe expands and cools and the cosmic background radiation fades, Hawking radiation will eventually cause even Sagittarius A star to evaporate. The timescale for a black hole of 4 million solar masses to evaporate via Hawking radiation is approximately 10 to the power of 83 years. For context, The age of the universe is approximately 14 billion years, about 10 to the power of 10 years. Sagittarius A star will outlast the current universe by a factor that is incomprehensible to human thought. But it will not last forever. In the end, even the dark heart of the Milky Way will fade, slowly, silently, into the cold of a universe that has long since forgotten the warmth of stars. Part 12. The stars that orbit the darkness. S2 is not alone. Astronomers have catalogued dozens of stars in close orbit around Sagittarius A star, collectively known as the S stars, or the S cluster. Each is a gift of nature, a moving probe, provided free of charge, orbiting in the most extreme gravitational environment accessible to our telescopes. S2 was the first to complete a fully documented orbit, and the one whose 2018 periapsis passage confirmed general relativity. But other stars have now been tracked in comparable detail. S62 was for a time believed to have one of the shortest known orbits, just 9.9 years, screaming around the black hole at nearly 10% the speed of light at periapsis. If confirmed in those parameters, it would come closer to the event horizon than any other known star. Later analysis has found some uncertainty in its orbital parameters, and refined measurements are ongoing. S4711 and S4714 are among the fastest known stars in the S cluster, with S4714 reaching speeds approaching 12% of the speed of light at closest approach. Their orbits allow tests of general relativistic effects at distances from Sagittarius A star that probe the gravitational field more deeply than even S2. And in December 2024, researchers announced the discovery of the first binary star system orbiting close to Sagittarius A star. Two stars bound to each other, orbiting their common center of mass, while that center of mass itself orbits the black hole. A pair of stars dancing together in the most dangerous neighborhood in the galaxy. Their discovery opens new possibilities for measuring the properties of the black hole, the spin, the mass, the frame-dragging effect, with precision impossible from single stars alone. Some of these inner stars have been circling Sagittarius A star for billions of years. Born in star-forming regions, kicked inward by gravitational interactions over cosmic time, they have orbited the same dark anchor through the entire history of the solar system. They will keep orbiting for billions more. Generations of stars born and dying, all held in orbit by the same invisible center. Sagittarius A star doesn't care. It doesn't hurry. It doesn't rest. It is patient, invisible, silent, but absolute. Every star near the core bends to it. Every orbit, every trajectory, every motion shaped by its gravity. You can't negotiate with it. You can't escape it. We are bound to it, the quiet tyrant at the center of everything. Part 13. The gravity that holds a galaxy. A common misconception is that Sagittarius A star is what holds the Milky Way together, that the galaxy orbits the black hole the way the Earth orbits the Sun, that without it, the galaxy would fly apart. The truth is more subtle, and in some ways more remarkable. Sagittarius A star does not hold the Milky Way together by itself. Its 4 million solar masses, while enormous by human standards, represent only a tiny fraction of the galaxy's total mass. The Milky Way contains roughly 400 billion stars, with a combined mass of perhaps 300 billion solar masses. Sagittarius A star's 4 million solar masses is about 100,000th of the total stellar mass alone. Add in the gas, the dust, and, most significantly, the dark matter halo that extends far beyond the visible disk of the galaxy, and Sagittarius A star's contribution to the total gravitational budget becomes vanishingly small. The galaxy is bound by all of its mass, stars, gas, dust, and dark matter added together. Dark matter alone is thought to constitute about 85% of the total mass of the Milky Way's halo. It is dark matter, spread across hundreds of thousands of light years in a vast, invisible sphere, that provides the dominant gravitational scaffolding within which the visible galaxy sits. But Sagittarius A star does dominate the innermost region of the galaxy. Within a few light years of the galactic center, its gravity dominates all other contributions. It sets the rhythm of the closest stars, as we have seen with the S cluster. It anchors the very center of the galactic potential. It shapes the orbits of everything within its sphere of influence, a region extending perhaps a few parsecs from the center. And in that sense, quietly, relentlessly, it is the dark mark at the center of home. Not the glue that holds the galaxy together, but the fixed point around which the innermost heart of everything revolves. We orbit at 230 kilometers per second, fast enough to circle the Earth in about 3 minutes. But the galactic center is so far away that one complete orbit takes about 230 million years. Astronomers call this one galactic year, or one cosmic year. The last time our solar system was in this exact position in its galactic orbit, the Triassic period was just beginning. The first dinosaurs were appearing. The supercontinent Pangaea was beginning to break apart. No mammal had yet evolved. No flower had yet bloomed. The next time we return to this same spot, 230 million years from now, Earth might be unrecognizable. The continents will be in different positions. The oceans will have different shapes. Most species alive today will be extinct. New ones will have arisen. Our sun will be about 2 billion years older and noticeably brighter, bright enough that the Earth may be at the inner edge of the habitable zone. Through all of that, through the dinosaurs and the mammals, and the first humans, and the last humans, and whatever comes after, Sagittarius A star will still be there. Patient, invisible, silent, the dark heart of the Milky Way. Part 14, The New Vision, Polarized Light and Hidden Jets. The first image of Sagittarius A star, released in May 2022, was the beginning, not the end. 2 years later, on March 27, 2024, the Event Horizon Telescope collaboration announced something new. The first image of Sagittarius A star captured in polarized light. Polarized light is light whose electromagnetic waves oscillate in a single plane, rather than in all directions at once. When light is polarized around a black hole, it carries information about the structure of the magnetic fields threading through the surrounding plasma. Magnetic fields play a crucial role in the dynamics of matter near a black hole. They help channel infalling material, launch jets, and regulate the accretion process. But they are invisible in ordinary imaging. Only in polarized light do they leave a signature. The polarized image of Sagittarius A star revealed something extraordinary. Strong, organized magnetic fields spiraling from the edge of the event horizon. Structured fields, not the chaotic tangle that might be expected in a turbulent accretion environment. The pattern looked remarkably similar to the polarized image of M87 star, obtained shortly before. Maria Felicia de Laurentiis, EHT Deputy Project Scientist and Professor at the University of Naples, noted, with a sample of 2 black holes, with very different masses and very different host galaxies, it's important to determine what they agree and disagree on. The similarity of the polarization patterns in 2 black holes that differ in mass by a factor of 1,500 suggests something fundamental about the physics near event horizons in general. The organized magnetic field also hints at something else. It suggests that Sagittarius A star may harbor a hidden jet, a narrow beam of material ejected from the poles of the spinning black hole, driven by the interaction between the spin energy and the surrounding magnetic field. We have not yet directly detected such a jet from Sagittarius A star, but the magnetic field structure is consistent with one existing, perhaps oriented away from our line of sight, perhaps suppressed by the current low accretion rate. If and when more material falls toward Sagittarius A star, if the accretion rate increases, the organized magnetic field could serve as the conduit for a powerful outflow. The spinning black hole would extract its rotational energy through the Blandford-Zanarjek mechanism, driving plasma up the magnetic field lines and out along the rotation axis as a collimated jet. At 60% of the maximum spin, Sagittarius A star has enormous potential energy stored in its rotation. The question is whether the fuel ever arrives. Part 15. The Galactic Center Environment. Sagittarius A star does not sit in isolation. The Galactic Center is one of the most extreme environments in the Milky Way, crowded, violent, and strange by the standards of the quiet suburban spiral arm where our solar system resides. Within a few light years of Sagittarius A star, the star density is extraordinary. The stellar density near the galactic center is millions of times higher than in our neighborhood. Stars there are separated by fractions of a light year, rather than the 4 light years that separate us from our nearest stellar neighbor, Proxima Centauri. Among these close-packed stars are populations that should not, by conventional understanding, exist there at all. A disk of young, massive stars, hot blue stars that formed within the past few million years, orbits within 1 or 2 light years of Sagittarius A star. This is the paradox of youth at the galactic center. Young, massive stars form from the collapse of cold gas clouds. But near a supermassive black hole, tidal forces should shred those clouds before they can collapse. And yet there the stars are, young, hot, and close. How they formed remains an active research question. Some models propose that they formed farther out and migrated inward. Others suggest that in the extreme tidal environment, collapse is possible in dense clumps that resist disruption. Beyond the innermost stellar disk, the galactic center is threaded with massive molecular clouds, dense reservoirs of cold gas that are the raw material of star formation. The most massive of these, the Sagittarius B2 molecular cloud, contains about 10 million solar masses of gas and is one of the most complex chemical environments in the galaxy. Radio observations have detected dozens of organic molecules in this cloud, including amino acid precursors, hinting at the richness of interstellar chemistry in the galactic center. The galactic center is also a source of powerful X-ray and gamma-ray emission from both the hot gas around Sagittarius A star and from a population of X-ray binary stars. Compact objects in tight orbits with companion stars, stripping material from their companions and emitting X-rays in the process. The James Webb Space Telescope, in images released in November 2023, revealed never-before-seen features in the heart of the Milky Way. Thousands of previously uncatalogued stars, nebulae, and complex structures in unprecedented detail, confirming the extraordinary richness of the galactic center environment. Even more recently, in June 2023, astronomers discovered unexplained filaments of radio energy associated with Sagittarius A star, structures extending from the galactic center into the surrounding medium, whose origin remains unknown. They are unlike anything seen elsewhere in the galaxy. New features, new mysteries, new questions. The galactic center is still teaching us things we do not yet understand. Part 16. What we are. Passengers on a moving world. Right now, somewhere near the constellation Sagittarius, there is a black hole. You cannot see it with your eyes. You cannot point to it in the sky and say, "There." It is hidden behind 26,000 light years of dust and gas and distance and time. But it's there, and you have been circling it your entire life. So have your parents. So has every generation before you. So has every star you have ever seen. All of it, the whole spinning visible apparatus of the night sky, held in the embrace of something we couldn't even photograph until 2022, something we still cannot see as it is, only as it was. 26,000 years ago. You were born into motion, not just the motion of a planet spinning and orbiting a star, though that too, but motion in the grandest sense. 230 kilometers per second around the dark heart of a galaxy, along an orbit so vast it takes 230 million years to complete. You will not live to see a single degree of that orbit completed. In a human lifetime of 80 years, you trace less than a millionth of the arc. And yet the orbit continues. It has continued for 4.5 billion years, through every mass extinction, through every ice age, through the entire history of life on Earth, through the formation of the first cells in the ancient ocean, through the emergence of complex animals, through the age of the dinosaurs, through the first hesitant footsteps of our ancestors on the African savanna, through the construction of Newgrange and the pyramids and the Great Wall, through every word ever written, every song ever sung, every human life ever lived. The solar system has been orbiting Sagittarius A star through all of it. The orbit has never missed a beat. Sagittarius A star doesn't know we are here. It exerts no special attention on our solar system, no preference, no awareness. It is geometry, not personality. Mass curves space-time, and space-time tells mass how to move. The sun follows the curve. The planets follow the sun. We follow the planets. That is all. That is everything. And somehow that is enough to be astonishing. The dark heart of the Milky Way. Not the most massive black hole in the universe, not the farthest, not the brightest, but ours, the center of home, patient, quiet, inescapable, closing. You are orbiting it right now. You were orbiting it when you were born. You will be orbiting it when you are gone. Always turning, never arriving, always seeing it late, never seeing it now. The invisible thing at the center of everything. The thing you can't escape. The thing you have always been bound to. Sagittarius A star, the dark heart of the Milky Way. If this quiet journey through the center of everything has brought you even a moment of wonder, I am deeply grateful you spent it here. A gentle like, or a soft tap on subscribe, is not just support. It is encouragement to keep exploring these vast, quiet places in science, together. And if you are willing, I would love to know where you are right now, what time it is, what the sky looks like above you. Your words are like little stars that help guide the next journey. Until then, rest well, drift easily. And remember, somewhere above you, hidden behind the dust and the distance and the deep dark of 26,000 light years, something is turning, something ancient and enormous and patient, and it has been holding you all along. Part 17. What time feels like near a black hole. We have talked about the orbit, about S2, about the 16-year path, about the stars whipping around something invisible. But there is something deeper hidden in all of that orbital mathematics. Something that Albert Einstein predicted over a century ago, and that S2 confirmed in 2018. Time does not flow at the same rate everywhere. Near a massive object, near any massive object, time slows down. This is gravitational time dilation, and it is not a metaphor. It is not a philosophical proposition. It is a measurable, confirmed physical fact. Clocks placed at different distances from the Earth's surface tick at slightly different rates. GPS satellites must correct for it continuously. Their clocks run about 38 microseconds per day, faster than identical clocks on the ground, because they sit at a higher gravitational potential. Without the correction, GPS would accumulate errors of several kilometers every day. Near Sagittarius A star, gravitational time dilation is not a subtle effect. It is profound. At the innermost stable circular orbit, the closest distance a particle can orbit without inevitably spiraling inward, time passes at roughly 2/3 the rate it does far from the black hole. An astronaut orbiting at that distance would age at 2/3 the rate of someone far away. 1 year at the innermost stable orbit would be about 8 months for the astronaut, 4 months slower than the universe outside. Closer in, near the event horizon itself, the effect becomes extreme. A distant observer watching an object fall towards the event horizon would see the object slow asymptotically, its clock appearing to tick more and more slowly, its light red shifting into invisibility, until it seems to freeze at the horizon, an image stretched across infinite time from the outside perspective. But the infalling object experiences no such slowness. For it, the crossing is swift, unremarkable, and irreversible. S2 experienced this directly in May 2018. At periapsis, moving at 7,650 kilometers per second, at a distance of 1,400 Schwarzschild radii from Sagittarius A star, the light emitted by S2 was stretched by the equivalent of about 200 kilometers per second. The photons climbed out of the gravitational well and arrived at our telescopes carrying the imprint of the extreme environment they had escaped from. We detected the stretch. We measured the clock. And the clock ran slow, exactly as Einstein said it would. This means something strange and beautiful. S2, that blue-white star orbiting Sagittarius A star every 16 years, is, in a very real sense, slightly younger than it would be if it were far from the black hole. Every 16-year orbit it shaves a tiny fraction of time from its age. The gravitational field of Sagittarius A star is, imperceptibly, slowing the clock of everything in its vicinity. And since we orbit the Milky Way, and the Milky Way has a gravitational potential that includes the black hole's contribution, however small at this distance, our own clocks are very, very slightly affected too. At 26,000 light-years from the center, the effect is negligible. But it is not zero. We are in the gravitational field of a supermassive black hole, as we always have been, and time here, at this distance, ticks at a rate that is very, slightly different from time at absolute infinity. We live on a curve in space-time, all of us, always. And that curve was carved in its smallest and most distant way by the object you have been orbiting your entire life. Part 18, the Nobel Prize, the people behind the discovery. Behind every extraordinary scientific result, there are decades of extraordinary work by extraordinary people. The story of Sagittarius A star is also a story about 2 scientists and a decades-long parallel pursuit that changed how humanity understands its home galaxy. Reinhard Genzel was born in Germany in 1952 and spent much of his career at the Max Planck Institute for Extraterrestrial Physics in Garching, near Munich. Andrea Ghez was born in New York in 1965 and built her career at the University of California, Los Angeles. They led competing teams, the German-European team at the VLT in Chile and the American team at Keck in Hawaii, both aiming at the same patch of sky, tracking the same stars, pursuing the same question. The competition was real, and it was productive. Each team pushed the other. Each new result from one side prompted renewed effort from the other. Measurements were cross-checked. Methodologies were refined. Science worked the way it is supposed to work, through multiple independent lines of evidence converging on the same answer. Both teams tracked S2. Both watched it sweep past the black hole in 2002 and again in 2018. Both confirmed the mass. Both confirmed the gravitational redshift, and both were rewarded. In October 2020, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics jointly to Reinhard Genzel and Andrea Ghez, each receiving a quarter share, for the discovery of a supermassive compact object at the center of our galaxy. The other half of the prize went to Roger Penrose for his mathematical proof that black hole formation is a robust and inevitable prediction of general relativity. Work done half a day century earlier that had laid the theoretical foundation for everything the Galactic Center observations confirmed. It was the fourth Nobel Prize ever awarded to a woman in physics, a fact that speaks both to the achievement and to the continuing imbalance in the history of the field. Andrea Ghez, in her Nobel lecture, described the Galactic Center as the best laboratory in the universe for testing the physics of gravity near a supermassive black hole, a laboratory that nature had constructed for us and that required only the patience and the instruments to read what it had written. Genzel and Ghez spent more than 25 years building those instruments, refining the observations, and following the stars year after year. It is one of the longest sustained experimental campaigns in the history of astronomy. Two teams, on opposite sides of the world, watching the same invisible thing. And between them, proving that it was there. Part 19, the Event Horizon Telescope, how we photographed the shadow. Photographing the event horizon of a black hole was, for most of the 20th century, considered effectively impossible. The angular size of even a nearby supermassive black hole, as seen from Earth, is simply too small for any conventional telescope to resolve. Sagittarius A star's event horizon, at 26,000 light-years, subtends an angle of about 52 microarcseconds. For context, 1 arcsecond is 1/3600th of a degree. 1 microarcsecond is 1/millionth of that. 52 microarcseconds is roughly the angle subtended by a donut placed on the surface of the Moon, as seen from Earth. Conventional optical telescopes cannot achieve this resolution. Even the largest optical telescopes have angular resolutions measured in tens of milliarcseconds, 100,000 times too coarse. The only way to achieve the required resolution is to use radio interferometry, combining signals from multiple telescopes separated by the largest possible distance. In radio interferometry, the angular resolution of the combined array is determined not by the size of any individual dish, but by the distance between the most widely separated dishes, the baseline. The longer the baseline, the higher the resolution. To resolve Sagittarius A star's event horizon, you need a baseline roughly equal to the diameter of the Earth. The Event Horizon Telescope is exactly that. Not a single instrument, but a collaboration of 8 observatories at 6 geographical sites: Chile, Hawaii, Arizona, Mexico, Spain, and the South Pole, spread across the planet to form the largest baseline physically possible without leaving the ground. Synchronizing these observatories required atomic clocks accurate to a fraction of a trillionth of a second. The data from each telescope was recorded on high-capacity hard drives and physically shipped to correlation centers in the United States and Europe. There is no network in the world fast enough to transmit the data rates required. The South Pole Telescope, in particular, presented logistical challenges. It can only be reached by plane during the brief Antarctic summer, and its data drives had to wait months for the next available flight. The first observations of Sagittarius A star took place over 5 days in April 2017. The data required 5 years to process, involving the development of new computational algorithms, multiple independent analysis teams using different methods, and the generation of thousands of candidate images before the final result could be extracted. The image released in May 2022 is a landmark not just in astronomy, but in the history of observation. It is the first direct visual evidence of the black hole at the center of our galaxy. A bright ring of hot gas, bent into a luminous circle by the gravity of the event horizon, surrounding a dark shadow whose size and shape are consistent with general relativity's predictions for a 4 million solar mass black hole. The EHT collaboration involves over 300 researchers from around the world. No single person can claim credit for it. It is a monument to what happens when the global scientific community works together toward a single extraordinary goal. Part 20. Tidal disruption events. When stars die at the center, Sagittarius A star may be quiet most of the time, starved, dormant, waiting, but occasionally nature delivers a meal. A tidal disruption event, or TDE, occurs when a star wanders too close to a black hole, close enough that the difference in gravitational pull between the near side and the far side of the star, the tidal force, exceeds the self-gravity that holds the star together. At that point, the star is torn apart. Its material is stretched into a long stream, half of which escapes into space, and half of which falls back toward the black hole and forms an accretion disk. As this stellar material spirals inward, it heats to millions of degrees and emits a powerful flare of radiation, in many cases briefly outshining the host galaxy. We observe these events in other galaxies regularly. They are detectable across billions of light years. The innermost boundary at which tidal disruption can occur, the tidal disruption radius, depends on the mass of the black hole and the density of the star. For a Sun-like star approaching Sagittarius A star, the tidal disruption radius is about 100 times the event horizon radius. A star that wanders inside that boundary is doomed. Sagittarius A star is estimated to experience a tidal disruption event roughly once every 100,000 years. In the context of a galaxy that is 10 billion years old, that is frequent. The last major tidal disruption may have occurred within the past few million years, contributing to the population of stars and gas structures we now observe near the galactic center. We have also observed something called a tidal disruption precursor, the G2 cloud event of 2013 and 2014. Astronomers observed a compact cloud of gas, or possibly a young star enshrouded in gas, approaching periapsis with Sagittarius A star. There was enormous anticipation that G2's closest approach would trigger a visible accretion event, a brightening, a flare. The event was more muted than expected. G2 survived, somewhat distorted, without triggering a major outburst. But the episode confirmed that material does occasionally come close enough to influence the accretion environment. And it reminded astronomers watching from afar that the feeding of a supermassive black hole is not a steady, continuous process, but an episodic, unpredictable one. Stars are falling into Sagittarius A star, eventually, somewhere. They have been falling for billions of years. They will fall for billions more. The monster at the center of the galaxy is patient. It doesn't need to hurry. The stars come to it, given enough time. Part 21. What comes next? The future of Sagittarius A star science. The image of Sagittarius A star in 2022 and its polarized sequel in 2024 were the opening of a new era, not the conclusion of one. The Event Horizon Telescope is already being upgraded. New stations are being added, telescopes in Africa, in Greenland, in Antarctica, that will extend the baseline and improve the angular resolution further. The next generation EHT, known as NGEHT, aims to produce not just images but movies, time sequences of the event horizon that will reveal the dynamics of the orbiting plasma and the magnetic field in real time. Watching the ring of light around Sagittarius A star flicker and evolve over hours, rather than being averaged into a single static image. In space, the Gravity Plus project at the Very Large Telescope will extend the interferometric capabilities that confirmed general relativity in S2's orbit, pushing toward the detection of even smaller effects, including potentially the direct measurement of Sagittarius A star's spin rate through the subtle precession it imposes on the orbits of the closest stars. The Laser Interferometer Space Antenna, LISA, is planned for launch in the mid-2030s. LISA will be a space-based gravitational wave detector, sensitive to the frequencies emitted by merging supermassive black holes. Events like the ancient merger that UNLV researchers believe created Sagittarius A star will, in other galaxies, be happening today, and LISA should detect them, measuring the gravitational waves from collisions of million solar mass objects across billions of light years. Each detection will be a record of a galactic center being born, or reborn, a dark heart, taking its final form. The James Webb Space Telescope continues to peer deeper into the galactic center, revealing structures and populations invisible to previous instruments. Future observations may reveal the earliest stages of star formation in the tidal environment near the black hole, or detect new stellar populations whose origin challenges current understanding. And perhaps most intriguingly, astronomers continue to search for stars even closer to Sagittarius A star than S2, stars with orbital periods of months rather than years, tracing paths that would probe the gravitational field within a few hundred Schwarzschild radii of the event horizon. If such stars exist and can be tracked, they would allow measurement of the frame-dragging effect, the direct detection of space-time being dragged around by the rotation of Sagittarius A star. Not just confirming that the black hole is spinning, but measuring how it is spinning, the magnitude, the direction, the full characterization of the most intimate property of the dark heart of the Milky Way. Each new generation of instruments pushes the frontier. Each new observation adds another layer to our understanding of the invisible giant at the center of home. And each new question answered reveals 3 more questions waiting. That is the nature of science at its best. That is the nature of Sagittarius A star, an object that has spent 4 billion years at the center of our galaxy, and that we have been studying seriously for less than 50. We are at the very beginning. Part 22, the Fermi bubbles, the relic of past activity. 230 kilometers per second, 4 billion years of orbit. A quiet black hole, starved, patient. But how quiet has it always been? In 2010, NASA's Fermi Gamma Ray Space Telescope detected 2 enormous bubble-like structures emanating from the center of the Milky Way. They extend approximately 25,000 light-years above and below the galactic plane, nearly as far as the distance between us and Sagittarius A star. They are filled with high-energy particles, electrons and positrons, emitting gamma rays and radio waves. They are now known as the Fermi bubbles. Their origin is disputed, but the leading theories connect them directly to Sagittarius A star. One possibility is that the Fermi bubbles are the relic of a powerful outflow event. Jets or winds from Sagittarius A star, launched millions of years ago when the black hole was actively accreting at a much higher rate. The energetics required to inflate bubbles of that size suggest an outburst with a luminosity roughly equivalent to a moderately bright quasar, sustained over a period of millions of years. We saw earlier that ESA's Integral Observatory found evidence for an outburst roughly 300 years ago, orders of magnitude below quasar luminosity, but still a million times brighter than today's Sagittarius A star. The Fermi bubbles hint at something far more energetic in the deeper past. Another possibility is that the bubbles were created not by Sagittarius A star directly, but by an intense episode of star formation at the galactic center, a starburst in which millions of massive stars formed and died in rapid succession, their supernovae collectively driving a powerful wind into the galactic halo. Distinguishing between these scenarios requires better observations of the bubble interiors and boundaries which ongoing and planned missions are working to provide. Either way, the Fermi bubbles are a monument to the past activity of the galactic center. Physical evidence written across 25,000 light-years of space that something dramatic happened there in the not-so-distant cosmic past. The quiet black hole we observe today has not always been quiet. The dark heart has a history, and the history is written in the sky above and below us, in bubbles of energized gas that we can only now, with the right instruments, read. Part 23. Our place in the orbit. 230 kilometers per second. around a point 26,000 light-years away, in an orbit that takes 230 million years to complete. One orbit of the Milky Way, one cosmic year, 230 million Earth years. The Earth is about 4.5 billion years old. In that time, the solar system has completed approximately 19.5 orbits of the galaxy, 19.5 times around Sagittarius A star. On the first orbit, when the Earth had just formed from the cloud of gas and dust that also built the Sun, there were no continents, no oceans, no atmosphere. The surface was a global magma ocean, bombarded continuously by the remnants of the solar system's formation, still cooling, still congealing from liquid rock. By the second orbit, roughly 4 billion years ago, the first oceans had formed, and the first simple cells, single-celled organisms without nuclei, had appeared. Life had begun. The orbit continued. By the 10th orbit, about 2.5 billion years ago, photosynthetic bacteria had transformed the atmosphere. The great oxygenation event had occurred, the first mass extinction caused by life itself, as the oxygen produced by cyanobacteria poisoned the anaerobic organisms that had dominated the planet. The orbit continued. By the 18th orbit, complex animal life had exploded into diversity in the Cambrian explosion. Fish, arthropods, the ancestors of every animal alive today. The orbit continued. By the 19th orbit, about 230 million years ago, the Permian-Triassic mass extinction had killed 96% of all marine species and 70% of terrestrial vertebrate species. The most severe extinction event in Earth's history. The orbit continued. And now, in the first fraction of the 20th orbit, a fraction so small it barely registers, we are here, looking up at the sky, building telescopes, discovering the thing we orbit. We have traced less than 1/1,000,000th of this current orbit. We will not live to see a degree of it completed. But we know it is happening. We know it because of the patience of astronomers who looked at the same patch of sky year after year for decades, because of the mathematics of Kepler and Newton and Einstein, because of radio dishes in the desert and infrared cameras at the mountaintop and atomic clocks in the Antarctic, because of the Nobel Prize and the 26 years of observation that earned it, because of the 5 years of calculation that turned radio data into an image. We know where we are. We know what we orbit. We know its mass, its spin, its distance, its age. We have seen its face. That is not nothing. That is one of the most extraordinary achievements in the history of conscious life on this planet. A species that appeared, on cosmological timescales, essentially yesterday, figuring out that it lives in a galaxy, that the galaxy has a center, that the center is a black hole, and that they have been orbiting it since before they existed. You are made of atoms forged in ancient stars. You are living on a world that has orbited the galaxy 20 times since it formed. You are moving at 230 kilometers per second around an object, 4 million times the mass of the Sun. And you are the only thing in this solar system, as far as we know, that has figured that out. The dark heart of the Milky Way does not know you are here, but you know it is there. And in that knowing, in that 4 billion-year-old orbit, finally becoming conscious of itself, there is something that deserves a moment of quiet wonder. Part 29, Hawking Radiation and the Far Future. Stephen Hawking published one of the most surprising results in theoretical physics in 1974. He showed that black holes are not, strictly speaking, black. They glow, very faintly, at an extraordinarily low temperature, due to quantum effects at the event horizon. The mechanism is this. In quantum field theory, empty space is not truly empty. The vacuum is filled with pairs of virtual particles, particle and antiparticle, that briefly come into existence and annihilate each other almost instantly. This happens continuously everywhere in space, and under ordinary circumstances has no macroscopic effect. But at the event horizon of a black hole, something different can happen. A virtual pair is created just outside the horizon. One particle falls inward, crossing the event horizon and becoming part of the black hole. The other escapes outward, carrying energy away from the black hole. From the perspective of a distant observer, the black hole has emitted a particle, has radiated energy, without anything having escaped from inside the event horizon. The higher result is thermal radiation, a spectrum of particles at a temperature inversely proportional to the mass of the black hole. Small black holes are hot and emit powerfully. Large black holes are extraordinarily cold. For Sagittarius A star, with a mass of approximately 4 million solar masses, the Hawking temperature is about 10 to the power of -14 Kelvin, far colder than any temperature in the observable universe. The cosmic microwave background, the faint afterglow of the Big Bang that fills all of space, has a temperature of about 2.7 Kelvin. Sagittarius A star is currently absorbing far more energy from the cosmic microwave background than it emits as Hawking radiation. It is growing, not shrinking. But as the universe continues to expand, the cosmic microwave background will cool. In the very far future, roughly 10 to the power of 15 years from now, 1,000 times the current age of the universe, the background radiation will have cooled below the Hawking temperature of Sagittarius A star. At that point, the black hole will begin to net radiate more than it absorbs. It will begin, imperceptibly slowly, to evaporate. The complete evaporation of a black hole of Sagittarius A star's mass via Hawking radiation takes approximately 10 to the power of 83 years, one followed by 83 zeros. For context, the current age of the universe is about 14 billion years, one followed by 10 zeros. Sagittarius A star will outlast the current age of the universe by 73 orders of magnitude. It will still be there when every star in every galaxy has burned out, when every atom of ordinary matter has decayed into radiation, when the universe has expanded so much that the distances between objects exceed the light travel time, when the universe has effectively fragmented into isolated regions that can no longer communicate. And then finally, after an incomprehensibly vast time, Sagittarius A star will evaporate, the last burst of Hawking radiation, a tiny flash of energy at the end of an epoch so long it has no name and then nothing. The dark heart of the Milky Way, the thing that held 4 billion years of orbits together, the thing we photographed, the thing we orbit, gone, returned to the quantum vacuum from which, in some sense, it came. Part 30. The information paradox. What happens to what falls in? There is a problem, a deep, unresolved foundational problem that sits at the intersection of general relativity and quantum mechanics. It is called the black hole information paradox, and Sagittarius A star sits at the center of it. In quantum mechanics, information is conserved. Every physical process, no matter how complex, no matter how much it scrambles or entangles or redistributes information, is, in principle, reversible. If you know the final state of a system precisely enough, you can calculate the initial state. Information is never destroyed. It is transformed, rearranged, hidden, but never lost. This is called unitarity, and it is one of the foundational principles of quantum mechanics. But consider what happens when something falls into a black hole. The physical details of the infalling object, its quantum state, its information, seem to be lost forever. Nothing from inside the event horizon can escape. When the black hole eventually evaporates via Hawking radiation, the radiation appears to be purely thermal, random, featureless, carrying no information about what fell in. If this is true, then black holes violate unitarity. They destroy information. and that would be a catastrophic violation of the foundations of quantum mechanics. Stephen Hawking spent decades arguing that information was indeed lost in black holes, that black holes represented an irreversible process, a true destruction of quantum information. Most quantum physicists found this deeply uncomfortable. In 2004, Hawking conceded the argument, acknowledging that information is probably preserved, though the mechanism by which it escapes remained unclear. The most developed proposal for resolving the paradox involves the concept of black hole complementarity. The idea that the same information exists in two places simultaneously, as seen from different frames of reference, but that no single observer can see both copies. From outside the event horizon, the information is encoded in Hawking radiation, slowly released as the black hole evaporates. From inside, the information falls to the singularity, but no observer can see both, so no paradox is experienced. A more radical proposal, developed by Ahmed Almehri, Donald Marolf, Joseph Polchinski, and James Sully in 2012, suggests that the event horizon is not the gentle, locally uneventful boundary that general relativity predicts, but instead a wall of high-energy radiation, a firewall that incinerates anything falling through. If the firewall proposal is correct, then the equivalence principle, one of the cornerstones of general relativity, is violated at the event horizon. The information paradox remains unresolved. It sits at the frontier of theoretical physics, tantalizing, demanding a synthesis of quantum mechanics and general relativity that we do not yet have. Every particle that has ever fallen into Sagittarius A star, every atom of every star, every photon of light that has crossed the horizon since the black hole formed billions of years ago. Where is that information now? Inside? Encoded in the Hawking radiation? Nowhere? We do not know. And the fact that we do not know is, in its own way, one of the most profound things about our current understanding of the universe. Part 31. The discovery of the name. Why a star? Sagittarius A star. The name sounds like it might refer to a star in the constellation Sagittarius. It does not. The convention in radio astronomy for naming compact sources uses the host region, followed by an uppercase letter indicating the subsource. Sagittarius A is the large radio-emitting region at the galactic center. Within it, the most compact and most unusual component was designated Sagittarius A, with an asterisk, a star in the typographical sense, to indicate its anomalous, non-thermal nature. The asterisk was assigned in 1982 by Robert L. Brown of the National Radio Astronomy Observatory, one of the two astronomers who had originally detected the source 8 years earlier. Brown noted that the strongest radio emission from the center of the galaxy came from a compact, non-thermal radio object embedded in a larger thermal source, and the asterisk was his notation to distinguish the two. It has stuck ever since. The pronunciation, Sag A star, is the one used universally by astronomers. The name is awkward by the standards of astronomical nomenclature. Most major objects have names drawn from ancient myth, from the names of their discoverers, or from systematic catalogues with easily pronounced identifiers. Sagittarius A star has none of that elegance. It is a radio astronomer's note, a typographical asterisk promoted by the weight of what it refers to the name of one of the most important objects in the history of astronomy. The star at the center of our galaxy, the thing that 4 billion years of orbits revolve around, is named after a footnote. Perhaps that is fitting. The universe does not name its most important features for our convenience. It leaves them hidden behind dust clouds and the limitations of our instruments, waiting for us to find them and give them whatever ungainly name happens to stick. Part 32. Gravity waves from the galactic center. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. two black holes, each about 30 times the mass of the Sun, spiraling together over billions of years and merging in a fraction of a second, sent a ripple through space-time that crossed 1 billion light-years and arrived at LIGO's twin detectors as a stretching and squeezing of space by less than 1,000th the diameter of a proton. It was one of the most extraordinary observational achievements in the history of science. Einstein had predicted gravitational waves in 1916, the same year he published General Relativity, and humanity had been searching for them for a century. LIGO detects gravitational waves from stellar mass black hole mergers, events involving black holes up to a few hundred solar masses. For supermassive black hole mergers, events involving millions or billions of solar masses, LIGO is not sensitive at the right frequencies. Supermassive black hole mergers produce gravitational waves at much lower frequencies, with wavelengths measured in light years rather than kilometers. Detecting them requires a detector with a much longer baseline, longer than any distance on Earth. That detector is the Laser Interferometer Space Antenna, LISA, a planned space-based gravitational wave observatory consisting of 3 spacecraft in a triangular formation, separated by 2.5 million kilometers, connected by laser beams. LISA is expected to launch in the mid-2030s, funded jointly by ESA and NASA. It will detect the gravitational waves from merging supermassive black holes anywhere in the observable universe. Events like the ancient merger that UNLV researchers believe created Sagittarius A star. When LISA detects a supermassive black hole merger, it will produce a characteristic gravitational wave chirp, a signal that sweeps upward in frequency as the two black holes spiral closer together and merge. The signal will carry precise information about the masses and spins of the two black holes, the distance to the event, and the geometry of the merger. Each detection will be a record of a galactic center in formation, a dark heart taking its final shape, billions of light-years away. And LISA will also search for continuous gravitational waves from extreme mass ratio in spirals, events in which small compact objects, including stars and small black holes, spiral into massive central black holes like Sagittarius A star. If a compact object is spiraling into Sagittarius A star today, LISA should detect the gravitational waves it produces, giving us the most detailed map of the space-time around the galactic center's event. Horizon that it is physically possible to obtain. Not an image, not a measurement, but a direct sensing of the curvature of space-time itself, rippling outward from the closest supermassive black hole to Earth. Part 33. Why we look. The human need to know. Why do we care about Sagittarius A star? It is not trying to kill us. At 26,000 light-years, it is too far away to pose any threat to the solar system. The tidal forces from the black hole are immeasurably small at this distance. The radiation it currently emits is negligible compared to what the Sun delivers to us every day. We are, by any practical measure, perfectly safe. And yet we spent 30 years tracking S2. We built a planet-sized radio telescope to photograph an object the angular size of a donut on the Moon. We awarded the Nobel Prize to the people who confirmed that the galactic center is a black hole. We are planning space missions to detect the gravitational waves from its ancient merger. Why? Part of the answer is practical. Understanding supermassive black holes and their role in galaxy formation and evolution is central to understanding how the universe came to look the way it does. The M-sigma relation, the correlation between black hole mass and galaxy bulge mass, suggests that these objects shaped the galaxies they inhabit. Understanding Sagittarius A star gives us a laboratory for understanding this relationship at a scale and resolution unavailable anywhere else. Part of the answer is epistemological. Sagittarius A star is the most extreme environment accessible to observation. The gravitational field near its event horizon is the strongest sustained gravitational field we can probe with real data. Testing general relativity in that field, as S2 has allowed us to do, advances our understanding of the deepest laws of physics. If general relativity were to fail in that extreme environment, it would be the most significant physics discovery in a century. It has not failed. Not yet. But the tests continue, and each one is a measurement that constrains the boundary of what we know. And part of the answer is simply this: we are a species that looks up. It is what we have always done. From the first humans who noticed that the stars moved in patterns, to the astronomers who tracked S2 year after year at the VLT, to the hundreds of scientists who processed 5 years of radio data to produce a single extraordinary image. We are driven, irreducibly, to understand where we are. Not because understanding it makes us safer, not because it makes us richer, not because it solves any immediate problem, but because we are, as Carl Sagan said, a way for the cosmos to know itself. And knowing ourselves includes knowing the invisible thing we orbit, knowing that it is there, knowing its mass, its spin, its distance, its age, knowing that we have been circling it since before we existed. That is why we look. That is why we keep looking. That is why the orbit is not enough. We must also understand it. Part 34. The scale of the orbit. A journey we never notice. Every day, without noticing, without any instrument, without any sensation at all, you travel an extraordinary distance around the center of the Milky Way. In 24 hours, the solar system moves about 20 million kilometers along its galactic orbit. Not its orbit around the Sun, its orbit around the galactic center. 20 million kilometers per day, in addition to the 30 kilometers per second Earth moves around the Sun. In addition to the half kilometer per second, the surface of Earth moves due to its rotation. You are inside a motion, inside a motion, inside a motion, and none of them feel like anything at all. In 1 week, the solar system travels about 140 million kilometers along the galactic orbit. That is roughly equal to the distance from Earth to the Sun. In 7 days of ordinary life, waking up, drinking coffee, going to work, sleeping, you cover 1 astronomical unit in the galactic direction. A distance that took humanity thousands of years to measure, and which the solar system covers in a week as a matter of routine. In a year, 365 days, the solar system covers about 7.5 billion kilometers in its galactic orbit. That is about twice the distance from the Earth to Pluto at its farthest point. You live 1 year. The solar system travels to Pluto and back again, in the galactic direction, while that year is happening. In a human lifetime of 80 years, the solar system travels about 600 billion kilometers along the galactic orbit. That is about 1/100th of a light year. In a full human lifetime, the solar system covers 1/400th of the distance to the nearest star, in the galactic direction. And the full orbit, all the way around, is 230 million years. The Earth is about 4.5 billion years old. In that time, the solar system has completed approximately 19.5 orbits of the galaxy. 19.5 cosmic years, each 230 million Earth years long. And yet we feel nothing. No sense of motion, no sensation of arc, no awareness that the night sky is slowly rotating, star by star, past a distant center. The orbit is so vast, and we are so small within it, that it is literally imperceptible. We know the orbit is happening only by looking outward, mapping the positions and velocities of stars around us relative to the galactic center, and deducing from their collective behavior the rotation curve of the galaxy. The orbit of the solar system around Sagittarius A star is not something we experience, it is something we infer, something we calculate, something we know with the mind, not the body. And that gap between what we know and what we feel is one of the stranger features of being a conscious creature in a universe that operates at scales far beyond our senses. Part 35. The Radio Sky. What Sagittarius A star looks like at different wavelengths. The image the Event Horizon Telescope produced of Sagittarius A star is a radio image, not visible light, not X-rays, not infrared. Radio waves with wavelengths measured in millimeters, bent and captured and combined by a planet-sized array of radio dishes. But astronomers observe the galactic center across the entire electromagnetic spectrum, and each wavelength tells a different part of the story. In radio wavelengths, the center of the galaxy blazes. The region around Sagittarius A star is filled with hot, magnetized plasma, electrons spiraling in magnetic fields and emitting synchrotron radiation, a form of radio emission that is the signature of extreme, high-energy environments. This is how Sagittarius A star was first discovered in 1974, as an anomalously bright, compact radio source that stood out from the diffuse radio emission of the surrounding galactic center region. At radio wavelengths, it is visible as clearly as a lighthouse in fog, because radio waves pass through the intervening dust and gas that blocks all other wavelengths. In infrared wavelengths, the galactic center is also accessible. The Keck Observatory and the VLT use infrared cameras precisely because they can see through the curtain that hides the galactic center from optical telescopes. In infrared, the S cluster is visible, the densely packed stars in close orbit around Sagittarius A star, and it is their infrared positions, tracked over decades, that provided the orbital data used to measure the black hole's mass. In X-ray wavelengths, NASA's Chandra X-ray Observatory reveals the hot gas captured by the black hole, material heated to millions of degrees as it falls inward, emitting X-rays as it does. Chandra's observations showed that less than 1% of the material entering the black hole's gravitational sphere of influence actually reaches the event horizon. Most is ejected before crossing the point of no return. In gamma-ray wavelengths, the Fermi Gamma-ray Space Telescope detects the energetic particles produced near the galactic center and stored in the enormous Fermi bubbles. These bubbles, 25,000 light-years tall, blaze in gamma rays, a testament to some energetic event in the galactic center's past. Each wavelength window opens a different view of the same object. Each reveals a different aspect of the physics playing out around 4 million solar masses of compressed space-time. Together, they build a picture no single instrument could produce alone, a multi-layered portrait of the invisible engine at the center of our galaxy. Part 36. The Galactic Year and Deep Time. 230 million years. One cosmic year, one lap around Sagittarius A star. The Earth is about 4.5 billion years old. In that time, the solar system has completed approximately 19.5 orbits of the galaxy. On the first orbit, when the Earth had just formed from the cloud of gas and dust that also built the Sun, there were no continents, no oceans, no atmosphere. The surface was a global magma ocean, bombarded continuously by the remnants of the solar system's formation, still cooling, still congealing from liquid rock. By the second orbit, roughly 4 billion years ago, the first oceans had formed, and the first simple cells had appeared. Life had begun. The orbit continued. By the 10th orbit, about 2.5 billion years ago, photosynthetic bacteria had transformed the atmosphere. The Great Oxygenation Event had occurred, the first mass extinction caused by life itself, as the oxygen produced by cyanobacteria poisoned the anaerobic organisms that had dominated the planet. The orbit continued. By the 18th orbit, complex animal life had exploded into diversity in the Cambrian explosion. Fish, arthropods, the ancestors of every animal alive today. The orbit continued. 66 million years ago, midway through the current orbit, the Chicxulub impact. The non-avian dinosaurs go extinct. mammals begin to diversify. 300,000 years ago, Homo sapiens appears in Africa. Right now, at this very moment, we are here, at a position in the 20th orbit that is approximately 20 millionths of the way from the start of that orbit. We have been paying attention for the last millionth of it, and in that millionth of an orbit, we figured out where we are. We looked up and recognized the shape of our galaxy. We built instruments that could see 26,000 light-years away. We photographed the object we orbit. That is perhaps the most extraordinary thing about being human, not the orbit itself, which has been happening for 4.5 billion years without our knowledge or participation, but the fact that in the brief and recent moment of our existence, we noticed. Part 37. A quiet giant in a universe of giants. The universe does not lack for black holes. Astronomers estimate that there are roughly 100 million stellar mass black holes in the Milky Way alone. The collapsed remnants of massive stars that have burned through their nuclear fuel and imploded. Some are isolated, orbiting the galaxy in silence, undetectable except when they happen to pass in front of a background star. Others are in binary systems, paired with a companion star, stripping material from them, accreting, flaring, emitting X-rays. But the supermassive black holes are something else entirely. Almost every large galaxy in the observable universe appears to host a supermassive black hole at its center. Not a coincidence, not a curiosity, but apparently a fundamental feature of how large galaxies form and evolve. The mass of a galaxy's central black hole correlates with the mass of the galaxy's central bulge of stars, a relationship known as the M-sigma relation, suggesting that the growth of the black hole and the growth of the galaxy are deeply intertwined. When a supermassive black hole is actively accreting, when it is a quasar, the energy it releases is enormous. Radiation, jets, winds, all pushing outward into the surrounding galaxy, heating the gas, suppressing star formation, regulating the growth of the galaxy itself. The black hole and the galaxy are in dialogue, a feedback loop that shapes both over billions of years. Sagittarius A star is currently too quiet to provide significant feedback to the Milky Way. It is in a low state, far from the powerful quasar phase that some galactic nuclei exhibit. But it was not always this quiet, as the Fermi bubbles attest, and it will not always be quiet. In the grand census of supermassive black holes, from dwarf galaxies with hundreds of thousands of solar masses to the giants like TON 618 with 66 billion, Sagittarius A star is unremarkable. A typical modest-sized supermassive black hole in an average spiral galaxy. Nothing special by the standards of the universe, and yet it is the one we orbit, the one whose face we have photographed, the one we have come home to. The universe is full of supermassive black holes, but ours is the only one that has ever had a species figure out that they live around it. Part 34. Dark matter and the invisible scaffolding of the galaxy. When we say that Sagittarius A star does not hold the Milky Way together by itself, we are pointing at something that took most of the 20th century to understand. The galaxy is heavier than it looks, far heavier, and the extra mass is something we have never directly detected, never imaged, never touched. We know it is there only because of what it does, because of the gravity it exerts on the things we can see. The story begins in the 1930s, when the Swiss-American astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster, a massive collection of galaxies about 300 million light-years away. He found that the galaxies were moving far too fast to be held together by the mass of all the visible stars. By his calculation, the cluster contained about 400 times more mass than could be accounted for by starlight. He called the missing mass dunkle materia, dark matter. The term stuck, even though the concept was largely ignored for decades. In the 1970s, astronomer Vera Rubin, working with Kent Ford, made a discovery that could not be ignored. She measured the rotation curves of spiral galaxies, the speed at which stars at different distances from the galactic center orbit. According to Newtonian gravity, stars farther from the center should orbit more slowly, just as the outer planets of the solar system move more slowly than the inner ones. Instead, Rubin and Ford found that the rotation curves were flat. Stars at the edge of the galaxy moved at roughly the same speed as stars close to the center. The only explanation was that there was far more mass distributed throughout the galaxy, and especially in an extended halo beyond the visible disk, than the visible stars and gas could account for. The Milky Way, it turned out, is surrounded by an enormous dark matter halo, a roughly spherical distribution of invisible mass extending far beyond the visible disk of stars and gas. The total mass of this dark matter halo is estimated at about 1 trillion solar masses, several times the mass of all the visible stars in the galaxy combined. If this estimate is correct, dark matter constitutes approximately 85% of the total mass of the Milky Way. Everything we can see, all the stars, all the gas, all the dust, Sagittarius A star itself, is only 15% of what is there. What dark matter is at the particle level remains one of the deepest unsolved problems in physics. It is not made of ordinary protons and neutrons. It does not emit, absorb, or reflect light, hence dark. It interacts with ordinary matter only through gravity. The leading candidates from particle physics include weakly interacting massive particles, or WIMPs, hypothetical particles with masses similar to atomic nuclei, interacting so weakly that they can pass through the Earth without interaction, and axions, far lighter particles originally proposed to solve a problem in the strong nuclear force. Despite enormous experimental effort, no dark matter particle has yet been directly detected. The dark matter halo of the Milky Way is filled with billions upon billions of these particles, and they pass through us continuously, through the walls of this room, through the planet beneath, through our bodies, without leaving any trace. Simulations of structure formation in the universe show that dark matter is not a passive background. It is the scaffolding around which ordinary matter, gas, stars, galaxies, assembles. The filamentary structure of the cosmic web, the vast network of galaxy clusters and voids that stretches across the observable universe, is the shape of the dark matter distribution, with ordinary matter settling into the gravitational potential wells that dark matter has carved out over billions of years. Without dark matter, galaxies as we know them would not form. The Milky Way would not exist. The Sun would not have formed. The Earth would not be here. And Sagittarius A star, sitting at the center of the Milky Way's dark matter halo, anchors not just the visible galaxy, but the deeper invisible structure within which the visible galaxy is embedded. The center of the orbit you are on right now is a point defined not just by Sagittarius A star, but by the collective gravity of everything in the Milky Way, including the trillion solar masses of dark matter you cannot see. Part 35. The Sound of the Galactic Center. We speak of the galactic center as silent, the dark heart, the invisible thing, the quiet tyrant. And at optical wavelengths it is indeed dark and silent to human eyes. But in other wavelengths, in other modes of detection, the galactic center is extraordinarily noisy. In radio waves it blazes. The synchrotron radiation from spiraling electrons, the thermal emission from hot ionized gas, the compact intensity of Sagittarius A star itself, all of it combines to make the galactic center one of the brightest radio sources in the sky. Radio astronomers who point their telescopes toward Sagittarius see in their data a complicated and intense brightness distribution that reveals the structure of the galactic center in extraordinary detail. The molecular clouds, the ionized gas, the compact sources, and at the heart of it all, the compact, intense, unmoving radio source that Bialik and Brown first recorded in 1974. In X-rays, NASA's Chandra X-ray Observatory has spent 2 decades mapping the galactic center with extraordinary patience, building up exposure times that reveal structures invisible in shorter observations. The resulting images show thousands of point sources, X-ray binaries, cataclysmic variables, the remnants of supernovae, embedded in a diffuse glow of hot gas, with the intense nucleus of Sagittarius A star shining at the center. Occasionally, a bright X-ray flare erupts from the nucleus, lasting hours, brightening by a factor of hundreds and then fading, a brief window into the accretion activity that is usually too faint to see. In gamma rays, the Fermi Gamma Ray Space Telescope sees something different. The extended emission from the Fermi bubbles, the diffuse background of energetic particles filling the galactic halo, and what appears to be a concentration of gamma-ray emission near the galactic center that some astronomers have tentatively associated with dark matter annihilation. If dark matter particles occasionally annihilate each other in the dense environment near the galactic center, they would produce gamma rays at characteristic energies, a potential signature of the particle physics underlying dark matter. The signal is currently uncertain, consistent with known astrophysical sources but also consistent with a dark matter contribution. Future measurements may resolve the ambiguity, or they may not. The galactic center hides its secrets carefully. In gravitational waves, LIGO has not yet detected anything from the galactic center. Stellar mass events near the galactic center would be at the edge of its sensitivity. But LISA, when it launches, will be capable of detecting gravitational waves from extreme mass ratio inspirals in our own galactic center. The slow inspiral of compact objects into Sagittarius A star, a signal that would allow direct mapping of the spacetime near the event horizon with a precision that no other technique can achieve. The galactic center is not silent. It speaks in every language the universe has: radio, infrared, optical, X-ray, gamma ray, gravitational. We are only beginning to learn to read all of them simultaneously. Part 36. What it would look like to be there. Imagine for a moment that you could somehow be transported to the neighborhood of Sagittarius A star, not into the event horizon, but to within a few light years of it. Close enough to feel its presence, close enough to see it. The first thing you would notice is the stars. The stellar density near the galactic center is millions of times higher than in our neighborhood. The night sky, if you were on a planet orbiting one of the S stars, if such a planet could survive the extreme environment, would be blazing. Not the familiar scattered points of our night sky, but something closer to the Milky Way band. But everywhere, a sky so full of stars that the darkness between them would be the exception, not the rule. The combined light of the surrounding stars would illuminate even the darkest night, far brighter than the full moon in our sky. The second thing you would notice, if your instruments allowed, would be Sagittarius A star itself, not visible to the naked eye at optical wavelengths. There is still gas and dust near the galactic center that absorbs optical light. But in infrared, in radio, it would be unmistakable, an intense compact source, unmoving against the background of swirling stars, surrounded by the glowing accretion disk that the Event Horizon Telescope has photographed. At a distance of a few light years, the event horizon would still be tiny by angular standards, smaller than a planet would appear from here. But the ring of hot gas around it, the accretion disk, would glow intensely in the infrared and radio, a beacon at the center of everything. As you moved closer, to within light hours of the event horizon, the effects of general relativity would become apparent. Nearby stars would appear shifted in the sky, their light bent by the gravitational field. The black hole would be large in the sky now, a dark shadow surrounded by the blazing ring of bent light. Time itself would be running slightly slower for you than for an observer far away. The gravitational redshift would be measurable. The frame dragging, the dragging of space-time itself by the rotation of the black hole, would impose a slow rotation on any free object that did not actively counteract it. You would be inside the ergosphere of a rapidly spinning black hole, in the region where space-time itself is rotating faster than the speed of light allows anything to remain stationary. Escape would still be possible. You are outside the event horizon, but only with effort, only by actively fighting the current of rotating space-time. The experience would be that of being in the world's most extreme river, where even standing still requires constant swimming against the flow, and the dark shadow in the center of the ring would grow, not because you are approaching the horizon, you are maintaining a safe distance, but because you have come close enough that the shadow fills a visible portion of the sky. The thing you would be looking at is not merely darkness, it is an absence, a hole in space-time through which everything that enters is lost to the outside universe forever. Beneath that darkness, 4 million solar masses are compressed into a singularity that the laws of physics cannot describe. Beyond that ring of light, every photon is spiraling inward, caught in the geometry of the most extreme gravitational field in the accessible universe. You would be looking at the center of our galaxy, at the thing we have orbited for 4 billion years, at the dark heart of home. Part 37, What We Know and What We Don't. We have come a long way tonight. From the first radio signal detected in 1974 to the first image in 2022, from the orbital tracking of S2 to the Nobel Prize, from the question of what lurked at the galactic center to the confirmation of its mass, its spin, its distance, its age. Let us take stock. What we know about Sagittarius A star. We know its mass, approximately 4.3 million solar masses, determined with exquisite precision from the orbital dynamics of S2 and other S stars, confirmed independently by multiple teams using different methods. We know its distance, approximately 26,000 light-years, or 8 kiloparsecs, consistent with independent measurements from multiple techniques. We know its spin, approximately 60% of the maximum possible spin rate, from the 2024 Chandra and VLA study by Daly and colleagues. We know its apparent size in the sky, an event horizon shadow of approximately 50 microarcseconds, imaged by the Event Horizon Telescope in 2022. We know it is currently in a low accretion state, feeding at a rate far below its potential, producing luminosity that is 1 trillion times fainter than a typical quasar. We know it flares occasionally, brightening by factors of hundreds in X-rays, by a factor of 75 in near-infrared as seen in 2019. We know it has strong, organized magnetic fields threading the accretion region, as revealed by the 2024 polarized light image. We know its rotation axis is misaligned with the Milky Way, suggesting a past merger with another supermassive black hole. We know general relativity is confirmed in its vicinity, gravitational redshift at 5 sigma, Schwarzschild precession at 5 sigma, from S2's orbital data. What we do not know how Sagittarius A star formed or what its earliest history was. We do not know the exact details of the past merger, when it happened, how massive the other black hole was, which satellite galaxy it came from. We do not know whether the gamma-ray excess at the galactic center is a signature of dark matter annihilation or a conventional astrophysical source. We do not know whether a jet exists, hidden, suppressed, oriented away from us, or whether there is truly no jet at present. We do not know what happens at the singularity inside. Our physics breaks down there. We do not know how information is preserved when matter falls in. The information paradox is unresolved. We do not know what Sagittarius A star looks like right now, only how it appeared 26,000 years ago. The list of what we know has grown enormously in 50 years. The list of what we do not know has not shrunk. It has grown alongside it. Every answer reveals new questions. Every image, every measurement, every confirmation of theory opens another door into the unknown. That is, in the end, the most honest thing that can be said about Sagittarius A star. We know it is there. We know we orbit it. We know what it weighs and how fast it spins. We have seen its face, and we are still, in the deepest sense, only at the beginning of understanding it. Part 39. Polarized light and the structure of magnetic fields. When scientists talk about the magnetic field around Sagittarius A star, they are not speaking metaphorically. The magnetic field is real, physical, measurable. Lines of force threading through the hot plasma that surrounds the event horizon, shaping the flow of matter, channeling the accretion, potentially launching jets. It is one of the most important physical quantities in the environment of any black hole, and for most of the history of black hole astronomy, it was invisible. Not anymore. When light passes through or is emitted from a region with a strong, ordered magnetic field, the electromagnetic waves can be forced to oscillate in a preferred plane. They become polarized. The direction of that polarization encodes information about the direction and strength of the magnetic field that produced it. By mapping the polarization of the light in the ring around Sagittarius A star, scientists can map the structure of the magnetic fields near the event horizon. This is exactly what the Event Horizon Telescope collaboration did, in observations published in March 2024. The polarized image of Sagittarius A star revealed something that surprised even the team members who had expected some degree of organization. The magnetic fields near the event horizon are not chaotic and tangled, the way you might expect magnetic fields to be in a hot, turbulent accretion disk. They are strong, ordered, and organized in a spiral pattern that threads inward from the ring toward the event horizon. Strikingly, the pattern closely resembles the polarized structure observed around M87 star, the much larger black hole imaged in 2019. M87 star is 6.5 billion solar masses. Sagittarius A star is 4 million. They differ by a factor of over 1,000 in mass, yet their magnetic field structures, near the event horizon, look remarkably similar. This similarity suggests something fundamental, that the physics of accretion and magnetic field organization near a black hole event horizon is governed by universal principles, not by the specific mass or environment of the individual black hole. The same underlying physics operates at scales differing by 3 orders of magnitude. The organized magnetic field also carries a specific implication about what Sagittarius A star might be capable of. Strong ordered fields threading the event horizon of a rapidly spinning black hole are the ingredients for a jet. Through the Blandford-Zenarczyk mechanism, a process by which energy is extracted from the rotation of the black hole itself and channeled along the magnetic field lines, an ordered field can launch powerful outflows from the poles of the black hole. M87 star has such a jet, one of the most famous structures in radio astronomy, stretching for thousands of light years from the galactic center of M87. We have not yet detected an equivalent jet from Sagittarius A star, but the magnetic field structure is consistent with one. Perhaps it exists, oriented away from our line of sight. Perhaps it is suppressed by the current low accretion rate. Perhaps if more material falls toward the black hole, the jet will activate, and the dark heart of the Milky Way will, for a time, become something far more dramatic than it is today. A beacon, visible across millions of light years. Our galaxy's own version of what we see in M87. The quiet tyrant at the center of everything, briefly, powerfully, spectacularly awake. Part 40. the long silence of the dark heart. There is a quality to Sagittarius A star that defies easy analogy. It is not violent in its current state. It is not blazing. It is not consuming stars every year or outshining the galaxy. Most of the time, by the standards of active galactic nuclei, it is almost nothing. A whisper, where other galactic centers are shouts. A held breath, where others exhale continuously. And yet it is 4 million solar masses. It has been there for billions of years. It shaped the galaxy we live in. It holds the innermost stars in their extraordinary orbits. Its gravity has tested and confirmed Einstein's general relativity in the most extreme accessible laboratory in the universe. Its magnetic fields, ordered and strong, are poised to launch a jet if the fuel ever arrives. Its spin stores energy equivalent to millions of stellar explosions, waiting to be released. The silence is not absence, it is potential. There is a long scientific tradition of anthropomorphizing black holes, speaking of them as monsters, as devourers, as hungry engines. Sagittarius A star inverts that image. It is the quiet one, the patient one, the one that has sat at the center of this galaxy for 4 billion years and mostly refrained from consuming everything around it. Not because it lacks the ability, it has the mass, the spin, the magnetic fields, but because the material has not arrived in sufficient quantities. The galaxy feeds it slowly, sparingly on its own terms. In this way, Sagittarius A star is perhaps the most realistic portrait of what most supermassive black holes are, most of the time, not the blazing quasars we see at cosmological distances, but quiet, starved engines at the centers of quiet, evolved galaxies. The quasars were the youth of the universe, the active, consuming, blazing phase of galactic center evolution. What we see in Sagittarius A star today is the middle age, the settled, quiet, patient phase that most supermassive black holes eventually reach. And from here, 26,000 light-years away, we watch it, not with awe at its violence, because there is no violence to observe, but with something quieter, the recognition that this object has been the fixed point of our world's orbit for longer than life has existed on this planet, that it will continue to be the fixed point long after we are gone, that in knowing it, in having measured it and imaged it and confirmed its nature, we have done something that no other species, as far as we know, has ever done. We have found the center of home. Part 38. What we know and what we don't. We have come a long way tonight. From the first radio signal detected in 1974 to the first image in 2022. From the orbital tracking of S2 to the Nobel Prize. From the question of what lurked at the galactic center to the confirmation of its mass, its spin, its distance, its age. We know its mass, approximately 4.3 million solar masses, determined with exquisite precision from the orbital dynamics of S2 and other S stars. We know its distance, approximately 26,000 light-years. We know its spin, approximately 60% of the maximum possible spin rate, from the 2024 Chandra and VLA study. We know its event horizon shadow, approximately 50 microarcseconds, imaged by the Event Horizon Telescope in 2022. We know it is currently in a low accretion state, feeding at a rate far below its potential. We know it flares occasionally, brightening by factors of hundreds in X-rays. We know general relativity is confirmed in its vicinity, gravitational redshift and Schwarzschild precession, both at 5 sigma from S2's orbital data. What we do not know. We do not know how it formed or what its earliest history was. We do not know the exact details of the past merger, when it happened, how massive the other black hole was. We do not know what happens at the singularity inside. Our physics breaks down. There. We do not know how information is preserved when matter falls in. The information paradox is unresolved. We do not know what Sagittarius A star looks like right now, only how it appeared 26,000 years ago. The list of what we know has grown enormously in 50 years. The list of what we do not know has grown alongside it. Every answer reveals new questions. Every image opens another door into the unknown. That is the most honest thing that can be said about Sagittarius A star. We know it is there. We know we orbit it. We have seen its face. And we are, in the deepest sense, only at the very beginning of understanding it. Closing. You are orbiting it right now. You were orbiting it when you were born. You will be orbiting it when you are gone, always turning, never arriving, always seeing it late, never seeing it now, the invisible thing at the center of everything, the thing you can't escape, the thing you have always been bound to. Sagittarius A star, the dark heart of the Milky Way. Not the most massive black hole in the universe, not the farthest, not the brightest, but ours, the center of home, patient, quiet, inescapable. Sagittarius A star was there before us. It shaped the galaxy that made the star that made us. It will be there long after us. It does not need us. It does not know we are here, but we know it is there, and we know what it is, and we are still going around it, as we always have been, as we always will be. We are, as Carl Sagan said, a way for the cosmos to know itself. And one of the things the cosmos has come to know, through us, in this brief recent moment of our existence, is the dark heart at the center of our home. A planet, orbiting a star, orbiting a supermassive black hole. And the things living on the planet figured out that the black hole was there. That is not a small thing. That is perhaps the largest thing. If this quiet journey through the center of everything has brought you even a moment of wonder, I am deeply grateful you spent it here. A gentle like or a soft tap on subscribe is not just support. It is encouragement to keep exploring these vast, quiet places in science together. And if you are willing, I would love to know where you are right now, what time it is, what the sky looks like above you. Your words are like little stars that help guide the next journey. Until then, rest well, drift easily, and remember, somewhere above you, hidden behind the dust and the distance and the deep dark of 26,000 light years, something is turning, something ancient and enormous and patient, and it has been holding you all along. We are the first generation of humans to know this with certainty, the first to have seen the image, to have measured the mass, to have confirmed the spin, to have watched a star complete a full orbit around the dark heart of our galaxy. We are the first to have proof, not belief, not mythology, not poetic metaphor, but hard measured physical proof that we live in a galaxy with a supermassive black hole at its center. That is a threshold crossed, a door opened, a knowledge that cannot be unknowed. Sagittarius A star will outlast every human civilization that ever exists. But we were here when it was finally seen. And in that seeing, something extraordinary happened. The orbit became aware of itself. That is what we are. That is what we have always been, without knowing it. Travelers on a vast, dark circuit, finally looking up, finally asking where the path leads, finally finding the answer at the center of everything, patient, invisible, ancient, and ours.